Hello, everyone. My name is Martin Sebor. I'll be giving the next talk on implementing static analyzers in the GCC middle end. Just a few words about myself. I'm a GCC toolchain engineer at Red Hat for the last three and a half years, and prior to that, I was a toolchain engineer at Cisco. My focus throughout my career as a GCC engineer has been on primarily security, static analysis, and diagnostic improvements. My contributions to GCC have been in the W-restrict warnings, the W-format overflow, and string-off overflow warnings that you may have run into in your experience with the compiler. So I'm to blame for those. My other area of focus has been over the last 20 or so years, standards development, both I started out as a C++ committee member and then joined the C committee and various other committees. So, keeping an eye on those areas of development and contributing there. My goals for this talk, I'd like to share some lessons that I've learned the hard way over the last few years with implementing warnings in the GCC middle end. I want to take this opportunity to highlight both opportunities that are in this area, and also the challenges that I've run into while doing my work. I'm passionate about this work, so I'm hoping to drum up some interest in future projects and enhancements in this area. And longer term, my sort of ulterior motive or longer term goal is to work toward eliminating bugs in software out there to enable interesting optimizations and take advantage of optimization opportunities that are currently unexplored in the compiler, and use those opportunities to uncover even more and more subtle, harder to find bugs in software. I should preface this talk also by saying that this is not a proposal to turn GCC into a full-blown static analyzer. This is rather, I'm trying to make an argument to make better use of the facilities that already exist in GCC, the optimization infrastructure, to help in detecting certain kinds of difficult to find bugs, usually involving some sort of undefined behavior in user code. As I said previously, the longer-term goal is to help improve the quality of the implementation as well as to improve the quality of the code that the implementation is used to compile. So why would one want to do static analysis in a compiler? Why not focus on existing static analysis tools or developing a new static analysis tool? Well, the compiler has a lot of infrastructure already and is required to provide infrastructure to detect constraint violations. It's required to do that by the standard issue error messages for constraint violations. But beyond that, there has been over the years increasing interest in building security in from very first stages of development. And not just security, but focus on all aspects of software quality, including safety, and simply just focus on finding bugs early in the development process. The traditional view in the C community and the early view in the C++ community that to trust the programmer doesn't really apply anymore. We've learned the hard way that security bugs can be exploited, and so trusting the programmer to always know what they're doing without giving them the right tools to find out when they don't know what they're doing or where they simply make mistakes doesn't really apply anymore. There has been increasing pressure over the last number of years from both within the development communities and from within software development communities. By development communities in the earlier term, I meant the GCC or LLVM compiler communities, to detect and also mitigate undefined behavior in the compiler. We all know intuitively that the earlier a bug is detected, the better. the cheaper it is. There have been a number of studies out there that put the number at maybe an order of magnitude, depending on the the stage of the software development cycle. So if you detect a bug after, say, you release a software product, it might be orders of magnitude, several orders of magnitude more expensive than if you detect it early on before you check it into the code base. The one number I've read that's kind of being tossed around is up to 5,000 times. It can be up to 5,000 times more expensive to fix a bug after software has been released than early on before it makes it into the code base. So obviously, the earlier we catch bugs, the better, and the cheaper they are to fix. The increased software complexity makes detecting bugs by traditional means like software inspection or peer review much less effective. There are existing methods or existing tools that help in detecting bugs, like dedicated static analysis tools that could be used instead. Unfortunately, static analysis in the form of a dedicated static analysis tools has a fairly high process and compile time overhead. It takes a lot of time to set up static analysis. It takes quite a bit of time to run static analysis. My previous employer, it took about a week to run static analysis on the entire code base. So obviously that's not feasible for very large projects, and some organizations even decided to abandon static analysis altogether. I read recently that Google doesn't use static analysis tools simply because the code base is so large that they can't afford the overhead. Dynamic analysis tools are also out there, and they're extremely helpful, but they have a huge or significant runtime overhead, and dynamic analysis doesn't run often enough, or sometimes it doesn't run at all. And when it does run, it exercises only a small, obviously a limited area of the code, and only with a very limited data set, whatever the test harness might throw at it, but it doesn't exercise all the code paths. So the earliest time to detect bugs is during compilation, before they are committed into the code base. Now, why would we want to implement static analysis in GCC? As I said before, the historical view, and that's both from a maybe standards perspective and also from within the GCC community itself, the view to trust the programmer isn't viable anymore. The programmer needs more help as software gets more complicated, more involved. GCC already provides many useful diagnostics in GCC front ends. Traditional has provided good quality diagnostic in the front ends. But GCC is also a very feature-rich and mature and optimizing compiler. As an optimizing compiler, it, as you know, has many deep flow analysis passes that are primarily used for optimization. Some optimizations already do try to detect instances of undefined behavior and try to mitigate those instances or deal with those instances in one way or another. But unfortunately, rarely by diagnosing it, or not always by diagnosing it. So there are many gaps, and I see those gaps as opportunities, as well as inconsistencies in the detection and mitigation and diagnostic strategies within GCC in the middle end. So these opportunities are there waiting to be exploited. And the natural way to exploit those opportunities is to expose those in the form of warnings, expose those users in the form of warnings. So the detection obviously raises the question of appropriate mitigation. If we do put an effort into detecting an instance of undefined behavior, what should the compiler then do with the code when we know that the code has undefined behavior? How do we mitigate it? There's also increasing pressure from users and from the industry and from other compilers to do all of these three things, to detect, diagnose, and mitigate instances of defects or undefined behavior. And in my view, it just makes sense to implement the static analysis checkers in some form, limited form, as I said, not a full-blown static analysis checker in GCC. It makes for a better compiler, higher quality implementation, and a more usable compiler. So with that as a background, the purpose of warnings in GCC, when you look up the definition of a GCC warning, it's defined as a diagnostic message that reports constructions that are not inherently erroneous, but that are risky or suggest there may have been an error. So the definition of GCC warning is that it's not necessarily worthy or doesn't warrant issuing compilation error without W error. The language may not permit it or doesn't call for an error. The definition also suggests that there may have been an error, which implies that warnings, by their very nature, could have false positives and false negatives, or may simply point out suspicious or risky code. So the goal of warnings in GCC is to help detect likely coding errors of all kinds without drowning users in too many false positives, too much noise. It is to strike a reasonable balance between false positives and false negatives, between soundness and completeness, to use the static analysis terminology. The general strategies in static analyzers and also in compilers to implement diagnostics, it can be described as either pattern-based or flow-based, depending on what type of an algorithm is used to detect violations of these rules. The pattern-based strategy or pattern-based static analysis rules are basically regular expressions on steroids. They tend to operate on declarations or on individual expressions, very simple expressions and constant values, or their types. In theory, the pattern-based approach is both sound and complete. It has a 0 rate of false positives and 0 rate of false negatives. It is capable of detecting all problems and is capable of not issuing any false alarms. So an ideal implementation of a rule or a checker like that would be suitable for a front-end implementation. And then we have flow-based analyzers or flow-based warnings, which depend on control or data flow analyses. And ideally, the analyses would be across the entire program. Sometimes, most of the time, they are limited to translation units, or they can be limited to individual functions. In the flow-based warnings, false positives and false negatives are unavoidable. It's just the nature of the beast because of NP completeness. So they are not, as a result, they are not suitable for the front end alone. They require some sort of additional analyses, which in GCC are provided by the middle end. There are also metric-based analyzers and metric-based diagnostics that are not going to be discussed, but they involve, for example, cyclomatic complexity and using cyclomatic complexity of a function to determine the likelihood of the function containing an error or a defect. So I mentioned true and false positives. I want to take a little bit of time to go over the definitions of true and false positives, both the quote-unquote formal definition and the less than formal definition that's used by most of us. So a true positive formally would be described as a diagnostic that's issued according to the design and documentation of the rule. That kind of makes sense. But it doesn't necessarily imply a bug. The fact that it doesn't imply a bug means that it can lead to a false alarm. In practice and informally, we tend to think of true positives as diagnostics for bugs. If I get a warning from a compiler that's telling me, hey, you might have a buffer overflow here, or you might have an integer overflow, and it's not true, and it's obviously not true, we will tend to think of it as a false positive. And that unfortunately carries a little bit of a stigma, social stigma, with implementing both static analyzers as well as warnings in the compiler. A false negative would be a missing diagnostic, one that should be issued according to the design and documentation, but isn't. That's also problematic, of course, depending on which community you come from. If you come from the safety community, you would definitely not want to see any false positives. So different communities with different focus have different priorities and different sensitivity to false positives false negatives or false positives. False positives are diagnostics that are issued contrary to the design and documentation. In practice and informally, they tend to be the diagnostics that users either don't agree with and don't find useful. They think they know what they're doing and they really do know what they're doing. They're simply writing code that tends to trigger the diagnostic, and they feel that they should be free to write that code without being inundated by diagnostics from the compiler or analyzer. And then there are true negatives, which are the obvious, have the obvious definition. So let's take a look at some examples. Here's an example of a true positive from the GCC front-end wchar subscripts warning, which is defined to warn if an array subscript has type char. This is a common cause of error, as programmers often forget that this type is signed on some machines. Now, if you look at the example, it uses char as an index to the masks array, and it triggers the wchar subscripts warning. And it's interesting to note that the warning is issued even when chars are unsigned in the type system. So the question might be, does that make it a false positive? Well, it depends. Coming back to my previous slide, it really depends on the definition. According to the definition, it's not a false positive. The warning is justified. According to your view, if you're targeting a machine with your software that has unsigned characters, then this warning is probably not going to be terribly useful. You might consider it a false positive. You don't care if you're not targeting machines where chars are signed. So it does depend on how the warning is, or the rule is defined, and on your personal view. Here's an example of a false negative, the logical op warning, which warns about suspicious use of logical operators, and also warns when the operands of a logical operator are the same. And in the example, you'll see that GCC will issue a warning for the first instance of the expression where the two operands are the same, but it won't issue a warning for the second expression, where the operators, depending on how strictly you interpret the definition of the warning, you could say that the operators are also the same, right? The first and the third operator of an OR expression are the same. There's a bug report on it. It has been accepted, acknowledged, but strictly speaking, this is not a false negative, because the operands of the OR expression are not the same, right? We have two OR expressions here, and the operands are not the same. So the checker is, strictly speaking, behaving according to the definition of the rule. Nevertheless, we feel, or whoever acknowledged the bug report, we feel that we agree with the claim that it's a false negative. We would like to get that second case diagnosed also. An example false positive, we have a type limits warning that warns when a comparison is always true or always false due to the limited of a data type, but it doesn't warn for a constant expression. And here we have a bug report that says, well, I have a constant expression here and I'm getting a warning. So that's, I think, a pretty obvious and non-controversial case where the warning should not be issued. So where does GCC implement warnings? Where does GCC issue warnings from? We can see warnings coming out of pretty much all stages of compilation, except I think for pre-processing. The warnings are implemented in front ends. The warnings are implemented in the middle end, including the gimplifier, usually only with optimization, but not always only with optimization. Warnings are emitted before or just before the expansion to the RTL, and warnings are also issued by individual backends, typically in response to invalid command line options like W attributes, and also when laying down assembly, which is sort of rare. So some advantages of front-end warnings. They're simple. They're based on, as I said earlier,
So you said except the preprocessor, but the preprocessor does warnings. So if it looks like, say, you've tried to write a C comment inside a C comment or things like that, it will complain it doesn't do what you probably meant.
Okay, so even the
preprocessor does things as well.
Okay, good to know. So essentially every stage of the compilation process issues some warnings. Some advantages of the front-end warnings, I think I already suggested that because of their pattern-based nature, working like regular expressions, they tend to be simple and are based on lexical or type system rules. They tend to be low noise, and that's by their very definition, very nature, they should be low noise. They should have a low rate of false positives. In practice, they don't have a zero rate of false positives, even though it would theoretically be achievable. It depends on the rule definition. We saw some examples. They are high precision. They have, in theory, again, no false negatives. But the false negatives or the absence of false negatives tends to come at the cost of false positives in some cases. Another advantage is also that they are stable and consistent. In the front end, they're not, for the most part, impacted by code transformations or optimizations. They're also independent of the target that you're compiling for, another big advantage. Again, for the most part, an example where they are dependent is the obvious type system dependencies, the size of longs versus size of ints and so on. They are, for users at least, they are easy to understand and debug. And they are also easily suppressed, which is both an advantage and disadvantage. In preparation for the talk, I did a survey of most, not all, GCC warnings, and I try to categorize them depending on which bucket they fall into. And this is not, I'm not claiming this is 100% accurate. In fact, I'm pretty sure it's not 100% accurate, but you can see two kinds of pattern-based front-end warnings that are implemented in GCC. This is about 43 of them. And so it's a fairly representative list. I try to separate those into type-based rules and lexical pattern-based rules in bold. So as you can see, a fairly large number of existing warnings implemented in the GCC front ends that are based on the pattern approach. There are also a fair number of other warnings that don't use the pattern approach, or that are implemented largely in the front ends that are, as a result, prone to false negatives and false positives. The warnings that are implemented in the folder, or partially implemented in the folder, are in light gray. The others in black are implemented fully in the front ends. So some, you can see that some collaboration between the front end and between the folder is required in order to get a decent rate of false positives and a decent rate of true positives. As we'll see in some examples later, it's not enough implementing a warning in the front end primarily and trying to utilize the folder is not sufficient to avoid all false positives and certainly false negatives. All the warnings on the first list are prone to both false negatives and false positives. The warnings on the second list tend to be more prone to false negatives, but you can create use cases or test cases where false positives are possible as well. And then we have another last bucket here, sort of a gray area depending on how you look at the rule, how you interpret the rule, what you'd like to get out of the checker. They may or may not be prone to false positives and so on. So the downsides of front-end warnings, they do have some noise, even though, like I said, in theory, they could be both sound and complete. In practice, they have a non-zero rate of false positives. They tend to be simplistic, not necessarily that the implementation of a front-end warning is simple, but rather that they tend to find superficial problems. They don't, because they have limited insight, they have no data or control flow analysis at their disposal. They can't see through complex expressions, complex statements involving data flow. They can't see through inlining and so on. So even though in theory they are both sound and complete, in practice they're not necessarily always chosen appropriately, and they tend to lead to false positives and false negatives. A few of the examples of false positives and false negatives. Here's an example of W format that leads to a false negative. Interestingly enough, there are two instances where W format would apply here, and it only applies or only triggers in one of the two instances. GCC tries to make an effort, even though the warning is implemented fully in the front end, it tries to detect the problem and successfully does so. In the first case, where we have the conditional operator, it doesn't detect the same problem in the second case that involves a separate declaration of the format string and a separate call to sprintf using that format string. So we end up with a false negative for the same problem that is successfully detected in the first case. The reason for that, I think I already mentioned, is there is no constant propagation from the declaration of f in the second case, the format string, to the use of the format string in the sprintf call. Here's an example of a false positive from the Wsign-compare warning, which is defined to or specified as a warning that could produce an incorrect result during the comparison between signed and unsigned values. And here we have a bug report, rather old bug report, that shows that we end up with a bogus Wsign-compare warning in an expression that where clearly the value of I cannot be negative because the first sub-expression prevents it. So this is the root cause here. Again, we have no value range propagation to see that the value of I is constrained to non-negative values here. Wswitch, yet another warning that's implemented largely in the front end, to warn whenever a switch statement has an index or enumerated type that lacks a case for one of the named codes of that enumeration. We have no GCC in the front end or in the folder has no access to the control flow or value range analysis, so it misses the fact that the unhandled, the case that it's not handled in the case statement, or the switch statement rather, is impossible as a result of the if condition. The shift count warnings are notoriously prone to false positives and negatives as a result of their inability to see more interesting dependencies than the folder provides. They are implemented both in the front end and partially in the middle end, in the folder in particular, but they have no access. Not necessarily don't have access to constant propagation. So we see a false negative for an expression that involves a non-constant value, even though the constant case is successfully detected. Wshift-count-overflow, we have a false positive. We have no, again, that warning is implemented very early, so no dead code elimination. We don't see that the shift expression doesn't get evaluated, and we end up with a false positive.
In fact, there's code in glibc softfp that works around this. So rather than writing an if statement for things like that, it does a conditional expression $? And uses quite large embedding statements and expressions using that GNU extension in order to avoid these sorts of warnings. Because if you write a conditional expression, then the front end does avoid warnings like this in a code that's in the false half of a conditional expression with a constant condition, but not if it's an if statement with a false constant condition.
Right, so the downside of these limitations, as Joseph mentioned, is that it forces workarounds on user code. Sometimes the workarounds might be simple, other times they're not so simple. So if, from my own experience, if I should give some guidance when to implement a front-end warning, it would be for purely lexical or type-based rules. As I said, those work well, and they theoretically at least have 100% true positive rate and 0 false positive rate. The warnings should be based on or independent of operand values, and you should consider when you're choosing a front-end warning compile time constants that are accessible in the front end rather than other constants that are derived as a result of various propagation passes, excuse me. And the warnings should be independent of control flow. And you should consider cases like unreachable code that we saw in the last example that Joseph spoke to. For everything else, it's worth considering a middle-end implementation or some kind of a combined implementation. This is not a claim that such an approach is necessarily always feasible, but it's worth considering. Otherwise, be prepared to deal with the unavoidable false negatives and false positive with a purely front-end based implementation of the warning. Of course, the middle-end warning approach is not without its challenges, and I'll talk about those later. So with that, let's look at some existing middle-end warnings in GCC. I try to split these up into, this is, I think, comprehensive list. We have about, I want to say 34 warnings here. We had about 44 purely front-end based warnings. So we have 34 middle-end warnings, some of which are partly implemented in the front end also. And those are the ones in the light gray font. Most of the others are completely implemented in the front end. Excuse me, in the middle end. They depend on either a control flow or a data flow. So many of you, I'm sure, know what the middle end is better than I do, but I think it's worthwhile to still point out what it is that I mean by when I say middle end. I consider the middle end to include all analysis and transformation stages between after parsing has completed, basically starting with the gimplification pass and until RTL generation, but not including RTL generation or RTL transformations. So it includes, the middle end includes all the constant propagation passes, all inlining passes, value range propagation, point of alias analysis, dead code elimination, dead store elimination, and so on. And as I said, the middle end, in my mind, ends with the RTL expansion. So this is what I will be referring to when I'm talking about the middle end warnings. So what are the advantages of middle end warnings? The obvious advantage is that the middle end warnings have access to pretty much all the GCC middle end analysis passes. There are some caveats to be aware of, and I think I'll have a slide on those later. The big advantage from a user standpoint is that middle end warnings can detect non-trivial bugs, including and involving a complex computation that spans multiple statements, loops, inline functions, crosses function boundaries, and with LTO that crosses translation unit boundaries. So for the middle end warnings, very complex heuristics are possible, which are obviously not possible, as we said, in the front end. When adding a middle end warning, I have put together a list of guidelines that I would recommend to follow based on my own experience. That there tends to be a preference among GCC developers and maintainers in particular for dedicated warning passes rather than kind of sprinkling warnings all over the place. I myself have violated that guideline, and I've been slapped over the hand a few times for doing that. And I can certainly see the benefits of kind of segregating warning into its own pass rather than polluting the entire compiler with the warning code. When introducing a new pass, and of course I should qualify that if you're enhancing an existing warning, then it makes sense to put it where the existing warning is rather than introducing a new pass unless you'd like to move the code. When introducing an entire warning pass, the one of the first questions to ask is when do you want to run it? At which stage in the passes.def file should you introduce that warning? Certainly earlier tends to be less effective. You don't have access to all the later optimization passes, but it tends to be subject to fewer interactions with those passes as well. So earlier, you may not be able to do as much but the trade-off is that the later you implement a warning, the more interactions with other passes, like sanitizers, for example, you might have to deal with. Another question to ask yourself is whether it makes sense to run the warning pass without optimization. Is there anything useful that the warning could provide to users at O0? And there certainly are warnings where it does make sense. The sprintf types of warnings, the W format overflow, do run without optimization as well as with. So you might be able to do a limited amount of work and provide a limited quality of implementation with O0. Of course, without the benefit of the nice passes like BRP and so on. Another question to ask yourself is, does it need to trigger before or during folding? Folding is, I have the impression that it's viewed as a sort of a utility layer within GCC, and it's certainly being called from different passes throughout the compilation process. So there tends to be a preference to avoid warning from the folder. It's not always possible. In certain cases, you lose the important information that you have access to in the folder. And so for certain kinds of warnings, there's just no other way than to warn from the folder. Do you expect the warning to be subject to false positives? And if it is, like the uninitialized versus maybe uninitialized types of warnings, consider a two-level option. Consider the warnings interaction with LTO and with sanitizers. LTO, just because of its nature of exposing more code to the warning, tends to tickle bugs in the warnings or even in the optimizers, or expose interactions that you may not be prepared for or may not expect without LTO. Sanitizers, we'll have an example on where the interaction with sanitizers makes things difficult. Another guideline is to certainly avoid issue duplicate warnings, so make use of the tree no warning, gimpel no warning flags to avoid those. You also need to consider the interaction with other warnings that may be issued by other passes. You don't want to necessarily introduce a warning, a new type of a warning for a construct such as a function call that has already been diagnosed and that's going to be diagnosed later on. Does the warning need to trigger during the expansion of macros defined in system headers? One of the warnings I implemented, the string op truncation and string op overflow type of warning that detects buffer overflows, certainly needs to be issued for calls to, for example, str-ncopy, even if str-ncopy is defined in a system header as a macro. So you don't want the system header definition of a macro like that in glibc to suppress a useful warning, an important and useful warning like that. So consider that. Should the warning be enabled by WAll or WExtra, or should it be disabled by default? Another big and not easy to answer question. Consider the suppression mechanisms. Either a different way of writing the code that you're trying to diagnose that the user is going to have to use to avoid false positives, or the Pragma GCC diagnostic, and be aware that the Pragma doesn't currently work very well for middle-end diagnostics. When documenting the warning, consider the issue of false positives and false negatives, and not only what a true false positive and false negative is, or how it's defined, but also how it's typically perceived by users. If the warning isn't useful, and if it's too noisy, and if it requires too many changes to silence in a code base, or if it's too difficult to suppress, it'll be considered a false positive, whether or not you like it, or whether or not the definition matches that expectation. What information to include in warnings? Well, first of all, read the diagnostic guidelines on the wiki. Make sure you provide sufficient detail to describe the problem. Avoid generalizations like, this is undefined. That's not helpful. Avoid guessing at the programmer's intent or suggesting a solution. If the suggestion is wrong, or if you guess the intent wrong, that the warning isn't going to be helpful. Include all relevant operand types, values, or ranges. The warning is triggered based on the values of these parameters. So make sure those are included in the diagnostic. because they're not necessarily always apparent from the code, even though GCC does a great job of printing the affected line of code, and it might even print the inline in context. The values of the arguments are not necessarily available. In fact, in middle end warnings, they're not going to be available. They're going to be obscured by the data flow or control flow. So make sure you include those in the warning. Use the inform call to reference relevant declarations rather than simply pointing to the expression that triggered the warning. The relevant declaration, for example, if the warning is operating on an array, might be far away from the point of the function call or access to the array that you're trying to diagnose, and it may not be obvious to the user what about that declaration is triggering the warning. The size of the array, for example, may not be, even though you print it in the diagnostic, it may not be easily discernible from the reference to the variable itself. This is especially important if the variable that's being accessed is in a different function than the access itself, or even in a different file as a result of function inlining. Consider localization issues. It's very easy to forget, and I've certainly made my share of mistakes. Introducing localization problems like byte versus bytes and using a simple ternary expression like this in the warning call, which will be eventually caught by the translators just before a release. But at that point, you'll be busy with fixing other more important problems, and so this is simply unfortunate and can be avoided. Make sure you print the inline in context. Use the %G and %K format specifiers in GCC as while they're there, unless they go away. And also, in terms of quality implementation, compare the message that you're issuing to other compilers. I think I talked too long, and there we go. So some of the examples of problems that you might run into is insufficient details. This is an example of a array bounce message that was issued by GCC. Some older versions of GCC, the quality has improved, but in this instance, we see that the array itself is being referenced by function f is declared in another function, possibly in a different translation unit. The values of the arguments that are propagated as a result of inlining and constant propagation are also somewhere else at another point. Yet the text of the warning doesn't mention any of that. And the underlining isn't ideal either. It doesn't make it very clear which index of the two is actually out of bounds, what the value of the index is, and where the declaration of the variable that's being accessed is. So this, in my view, this would be a warning that simply doesn't provide sufficient detail. We have recently improved things. Here's an example where I would like to think that has the right amount of detail. Perhaps the presentation leaves something to be desired. I'll leave that to you to judge. Okay, so here, sorry about that. Hopefully that'll. So here we have a buffer overflow as a result of the arguments being out of bounds and the length of the string being excessive for the size of the destination buffer. And the warning that the format overflow produces, I think, has sufficient amount of detail. It certainly describes the amount of data that's being written into the region, the size of the region, the overall amount of output. I think there is still room for improvement here, and I know David has been working hard to come up with various ways to maybe even visualize this in some kind of a graphical form, maybe ASCII art, to improve the error message.
Do our format warnings warn for the case where you're not internationalized or you're doing localization unfriendly printing? Like we could detect if you're picking two different format strings based on comparison against n equals 1.
No, they don't.
We should implement that. All right. Thanks.
Any other questions? I know I've been trying to go quickly. I have lots of slides, but this is a good time to ask questions.
Of course, a warning like that for format strings that aren't internationalization friendly would really need to take account of flow stuff, because sometimes, say, you've got, say, call to a GCC diagnostic function with a conditional expression, and by itself, whether or not it's n equals 1, it's still bad because xgetText will only extract the first format string for translation. But you need to detect, say, if the strings have been marked up with the g_ macro to extract the translation, and also if it's conditional expression and the strings are variables earlier in the function, well, you need to know whether those variables were marked up for extraction for translation or not. And to complicate things more, macros like g_ expand to not to do anything when they're macro expanded, because they're markup for xgetText rather than the compiler. So, and of course, you'd like this thing to be useful for things other than just GCC itself, and lots of programs put the calls to underscore to translate things in every call to the diagnostic function rather than the GCC approach of doing special things in the diagnostic function. So you need to be able to detect, is there a call, is the string marked up with a call to this macro that just expands to its argument, which is an interesting thing, because after pre-processing, we don't really have the information required to give such a warning.
I have a question about flow-based warnings. Does GCC provide the ability to run an SAT solver or something like that?
I'll just note that use of tree no warning is dangerous because it has a tendency to suppress other warnings as well. We have a number of bugs in Bugzilla currently about wrongly suppressed warnings.
Yes. So in many cases, using tree no warning simply doesn't work for the reason that Jason mentioned. It does work fairly well when the target of the warning is a library call, like a library built-in. In that case, there are no other expressions that he could tack it onto, and it does work to suppress multiple warnings. For example, if you introduce a warning in the folder using the tree no warning or Gimple no warning bit, then it works well.
I just want to ask if you could answer my previous question.
Sorry, I was distracted.
Yeah, okay. The question was, does GCC have any kind of solving support, like an SAT or a constraint-based solver that makes it easier to reason about flow problems?
Floating point problems?
Flow data, flow and combined control flow problems.
Other than the existing analysis passes, you're kind of on your own to follow the control flow and determine what goes where. So there certainly is for optimization purposes, but nothing specific for warnings. Right. So yeah, I'm not sure if I understood your question correctly, but there are instances where it's necessary for the warning. In particular, one warning that I add, it's necessary to follow the control flow after the, say, call to a string function like stir and copy, and see what the next statement is. And then in that case, I was basically left to my own devices to traverse the CFG to get to the point of the statement that I was looking for, whether it is there or not. Go with that. Okay. Okay. Sorry about that. So just quickly, here's an instance of a warning, and I am responsible for this warning. I'm happy to take credit for it if you believe that it has the right amount of detail, or I'm responsible for it if you believe that it could be improved. Here's a warning that I think could definitely be improved that I also happen to be responsible for. This is the W-restrict warning that tries to provide enough detail to the user to see what's going on, where that overlap in the memcopy call is. And so it essentially incorporates all the information that the warning has about the access into a single diagnostic. But I suspect that the ranges will make the warning somewhat difficult to understand and figure out despite the large amount of information here, might make it a little difficult to understand. It's a complicated problem. If you have suggestions for how to improve this, how to present it differently, David, ASCII art, that might be the way to go. So in the interest of time, I'm going to try to speed things up a little bit. Just a few bullet points on testing a middle-end warning. It's important to verify that the inlining context is included. If it isn't, the warning is essentially going to be useless when inlining is involved. So as I mentioned, use the %G and %K format specifiers, and in the test suite, use the grep expression using a DG message directive to look for the inlining context. Make sure that the operands are underlined as expected. That's also very important, and use the begin multiline output and end multiline output directives to look for the underlining. Beyond just the appearance of the warnings, to fully exercise the warning in Bootstrap, make sure you use profiled Bootstrap to look for false positives. That tends to typically expose bugs in the warning implementation, in my experience. Beyond just bootstrapping with GCC and running the test suite, try to build a few packages, at least the foundational packages, like glibc, GDB, and the Linux kernel, and look for unexpected warnings when you're introducing a new warning, in a completely new area. It does tend to lead to quite a few new instances of the warning, obviously, and you would hope that it would find bugs in the source code, but among those might also be false positives that you will want to look out for. Be also on the lookout for known problems that I will discuss later in the implementation and testing of the warning, and verify that the suppression mechanisms that you document or that you want to have working, make sure that those work. A few ideas for middle-end warnings to implement. Try to provide an extension to the string op overflow warning for user-defined functions to detect buffer overflows by user-defined functions, like a user-defined version of stir copy. It should be possible, and in fact, it's a work in progress of mine that I've been kind of forced to put on the back burner for a while, but it's a nice extension that users have asked for. A pass that David prototyped, but I don't think David's currently working on it, correct me if I'm wrong, is to detect malloc and free and new and delete calls, mismatches in those calls, or double free instances, memory leaks, and other common problems.
For malloc free, presumably again you want handle user-defined functions like xmalloc and such like.
Right, so when implementing a new warning, consider introducing annotations to help the compiler see through user-defined functions that are wrappers for library functions like attribute malloc and alloc size and so on. Other examples are detecting invalid pointer arithmetic. that currently GCC only detects invalid array bounds or array indices, so providing a detection mechanism to find bugs in pointer arithmetic would be useful. Consider C++ exception safety and writing a warning pass that detects common errors related to exception safety. And some of these warnings have also, or present also, optimization opportunities. They kind of go hand in hand. So if you implement the warning, think about providing, along with it, the optimization that the warning might, the optimization opportunities that the warning might expose. Passing unterminated arrays to string functions, that's something that I've been working on, and Jeff might have actually already checked in the meantime. Nevertheless, it's a common problem to pass an array that doesn't have a terminating null to a string function. So detecting those wherever possible would be helpful. A number of other ideas are on the list that I'm going to skip over in the interest of time again. So I talked about the benefits of middle-end warnings. There certainly are downsides. Without optimization, the middle-end warning tends to be pretty ineffective. Some can provide some utility. The sprintf warnings, like format overflow and format truncation, are capable of detecting some very simple cases that rely on or see only constant values, but they don't tend to trigger, obviously, on the more involved cases. Middle-end warnings are affected by optimization levels, and they can be affected by the choice of the target. So that tends to be a downside. They're not completely consistent from one target to the next or between optimization options. Middle-end warnings are influenced by or can be incompatible with sanitizers. And it would be nice to be able to use the undefined behavior sanitizer and also crank up warnings to detect as many problems in one shot as possible. Unfortunately, the instrumentation inserted by sanitizers does tend to trigger false positives or even false negatives in some cases. The false positives in the middle-end warnings tend to be more difficult to suppress than in the front end. So that's certainly something to consider. The current mechanism, Pragma GCC diagnostic, doesn't work very reliably for middle-end warnings. And based on the discussions I had here this week, it sounds like that should be solvable, but currently there is no solution. And middle-end warnings can be tricky to implement. They tend to involve multiple passes. Oftentimes, the interaction between passes has to be considered, so it can be a little bit challenging. What are the common challenges for middle-end warnings? Well, one of them is the dependency on optimization. There is very little benefit without optimization. Some passes within GCC that compute their own internal information store that information only for the duration of the pass and don't necessarily expose the information to other passes in the form of a nice API. So one example would be the object size pass that computes the size of an object that is being referred to by a pointer. The information is available within the pass itself, but it's not exposed to other passes, so the other passes don't benefit from that analysis. The string length pass is another pass like it that computes the lengths of strings that are dynamically computed by a program, but those lengths are not exposed to other passes. Therefore, the warning pass that sits outside of the strlen pass will not see those lengths. The sprintf pass has a similar problem. We're currently working on merging those two passes, but the general architectural constraint that passes that compute their own private information and don't share it with others, don't expose it to others, that does have to be taken into consideration when you're implementing a new warning. Which pass do I put it in? Or do I put it in its own pass, or do I put it in the string length pass and lose the benefit of object size, or vice versa? There is, due to design constraints and limitations, there is a lack of distinction in GCC between explicit and implicit casts, which then may be important in some cases in the warnings, but there is no way to get at that distinction because it doesn't exist. It's not preserved in the middle end. There's also information that is lost about the structure of data and data accesses. due to prior transformations. For example, memcopy or strcpy calls get folded into memref expressions, and the memref expressions don't expose as much information as you might like about the nature of the access. So the later in the process a warning is implemented, the more likely it is that an expression like a memcopy or strcpy call will have been folded, and you will not be able to detect the kinds of problems that you might want to detect. The pointer types in GCC, as I recently found out, is not as reliable as one might like. And the pointer provenance that you might have access to early on in the, as early as the front end or maybe the folder, tends to get eliminated, tends to get lost, and is not available in later passes. So of course, that presents problems for detection of things like buffer overflows. There's also tension between code analysis and optimization versus warnings. Optimizations tend to be focused on correct code, versus warnings tend to focus on finding buggy code. So where an optimization might be okay and perfectly acceptable and appropriate for an optimization pass to give up pursuing a certain type of an analysis, the warning pass might be interested and might benefit from pursuing that kind of analysis further to determine whether that code may or may not contain an underlying bug. The suppression support I already mentioned, and there are philosophical differences both within the GCC user community and within the GCC development community behind that present challenges for implementation of middle-end warnings. I think I'm out of time. I have plenty of time? Oh. Am I out of time, or do I have more time? Okay, I'll keep going unless somebody shuts me up. So some of the challenges, the examples of some of the challenges are on these slides. As an example, here's a folding instance of where a string length call is folded into an integer, and that reads to missing W array bounds kind of warning. We are calling string length with a variable with an index, and the index is, we know it's greater than 7 or greater, yet the string length pass or the warning passes do not detect the out of bounds access, and GCC in fact even folds the string length call into true, which somebody might find surprising. I certainly did. Why is that? Well, here's the piece of code that is actually behind the root cause of the problem, and I'm not sure how readable that is, but it shows you, it has a comment that dates back, as far as I can tell, to 1992, maybe beyond, that folds that expression, the string length expression, into a non-constant expression. The author of the code apparently considered the possibility that the index might be out of bounds, but decided that if it is, oh well, it's the programmer's fault. We're not going to worry about the possibility that the code is wrong and that the problem may not be detected. Now, the code, as I said, is so old that was well before the introduction of the VRP pass that would have been able to detect it. So GCC could do much better today with access to the range, the value of the offset. But because this is this folding is implemented very early on in the folder, in fact, we are unable to detect that kind of problem. So the only way to fix this is to defer the folding until a later stage, which in and of itself is somewhat controversial. Here's another example where folding early, and this is a folding of memcopy, gets in the way of diagnosing buffer overflow, an important security-related problem. GCC folds certain expressions, such as calls to strcpy, calls to memcopy, and where the strcpy call has access to the provenance of the pointer, in other words, the sub-object, which is the array A. It has 4 elements here. The memcopy call is explicitly excluded from these constraints. And so by folding one to the other, we lose the ability to detect the buffer overflow, the overflow of the first element into the second member of that struct, which in this case I chose a member function, or rather a function pointer, as a member of that struct to kind of drive home the point that this is a potentially very serious security problem that we would like to be able to detect, yet as a result of the folding to memcopy, we are unable to. Here's an example where I try to illustrate the unreliability of the pointer provenance. We end up failing to issue the string up overflow, except with fortify source. For this case of buffer overflow, we have a reference to either of the two members. One of them is an array of 3 characters. The second array, okay, I'll wrap it up. The second array has 5 elements, and we're clearly overflowing it. Yet the warning is missing, and here you can see the gimple that explains or that illustrates why it's missing. The L address pass, the gimple before the L address pass runs, does have the provenance capture here. So we still see the size, we're going to determine the size of the reference array. So at this point, we can still determine that a buffer overflow occurs. The provenance is preserved. But after the L address pass, those references get eliminated, and we end up with the reference that has plus on off, and the reference that has plus on off. And as, of course, is the larger object, we can no longer detect that the member object is being overflowed. I think with this, because I'm out of time, I'm going to wrap it up. I had a few other slides, but unfortunately, because of the technical problems, I apologize, not able to cover. I'm more than happy to answer questions after the talk or in email. Thank you very much for coming and for listening.